In this video, we will be looking at optimization problems that focus on optimizing time and distance. So for our first example, a man launches his boat from point A on a bank of a straight river 3 kilometers wide and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. He could proceed in any of 3 ways. Now, before I go through the 3 ways, I am going to draw a diagram to visualize this scenario. So this is one side of the riverbank, this is the other side. Let's say the man is here at point A, and this distance here, 3 kilometers. He wants to reach point B, let's say point B is here, and this whole distance is 8 kilometers, right there. Okay, here are the 3 ways that we could proceed. A, row his boat directly across the river to point C. So let's say this is point C. So we go directly across and then run to B. So that's option A. Option B, row directly to B. So go directly across. And option C, row to some point D. So let's say this is D here. Row there and then run the rest of the way to point B. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he row to reach B as soon as possible? Okay, so just a reminder here, since we're optimizing time. So we already know that the speed of someone is their distance divided by their time. So if instead I want to know the time, that's going to be distance divided by speed. So let's start with option A. Option A, he's going directly across for 3 kilometers to point C, and then he runs 8 kilometers. So his total time, it's 2 components. The first portion is a distance of 3, and he can row 6 kilometers per hour. So that's 3 kilometers divided by 6 kilometers per hour. Then he's going to run 8 kilometers at a speed of 8 kilometers per hour. And if we evaluate this, that's 1.5 hours. That's option A. Option B, row directly to B. Well, I need that distance from A to B. So I'm going to do a quick Pythagorean theorem here. The distance of AB is going to be, I'm going to take the square root from the very beginning, of 3 squared plus 8 squared. And just to keep my accuracy here, I'm just going to keep it as an exact value, and that's the square root of 73. So my time is going to be this distance, the square root of 73 kilometers, divided by the speed. And since it's just rowing, the speed is 6. So there it is, but if I want to compare it to option A, I am going to turn this into its rounded decimal, which is approximately 1.42 hours. So option B is already better than option A. But we still have to do option C. Now option C, we're going from A to D and D to B. Now we don't know what this distance from A to D is. So what I'm going to do, I'm going to add in a variable. And I'm going to say, I'm going to put X here. And the reason I'm going to put X there is because then I can get that length from B to D, and I can write it as 8 minus X. So for my let statement, I'm going to say let X represent distance CD. Now, my time is going to be the distance from AD divided by the rowing speed, that's 6, plus the distance from DB divided by the running speed, which is 8 kilometers per hour. Now I already have an expression for DB. For dB, I can write 8 minus x. So I'm just going to write that in for now. But what about from A to D? Well, if we look at what we have here, A to D creates this right triangle between x, 3, and AD. Just going to add in that that's a right angle. So I can find an expression for AD in terms of x by doing a little Pythagorean theorem on the side. So I'm going to do that. AD is equal to, again, I'm just going to go straight to my square rooting, and I know I only want the positive version of x squared plus 3 squared. So I'll just write 9. And now I can take this and plug it in for AD. Now I have an equation for time all about x, so I'll write t of x. And now we can go on to our regular optimization steps. Let me find the derivative of this so that I can then set it equal to 0 and find those critical points. Now, the value of x, as my little restriction here, can be anywhere between 0 and 8. So if x is 0, so that means D is right here where C is, that's just option A. So I don't even have to test it because I already know the time for option A. And if x is 8, that puts point D right on B, which is option B. So actually the restriction that we have on x there, that covers option A and B that we've already done. So when I do my test value, it's only going to be for my critical point. But let's go ahead and start on that derivative. So as a reminder, when you have something over that integer, it is just a fraction coefficient. So before I go to my derivative, I'm actually just going to write this as 1 over 6 square root of x squared plus 9 plus, and then 8 divided by 8 is 1 minus 1 over 8x. That looks a little nicer. Now I'll take the derivative. So for my first part, I am going to have a chain rule. So remember, the square root is the same as something to the power of a half. So I'm going to bring the 1/2 down, write the inside to the power of negative a half, and now the derivative of the inside is 2x. There we go. Now the derivative of 1 is 0, and the derivative of negative 1 over 8x is negative 1 over 8. And now I'm ready to set my derivative equal to 0 and clean this up. So when I clean this up, I am going to take this part with the negative exponent and bring it down. Now 1/2 times 2x is just going to be x, and then the 6 is down in the denominator, minus 1 over 8. Now I'll bring that 1 over 8 over to the other side, and then I'm going to cross multiply. So I have 8x equals 6 times the square root of x squared plus 9. I really want to get rid of that square root, so I'm going to raise both sides to the power of 2, which means 8x all squared will be 64x squared. And then 6 to the power of 2 is 36, and then the square root to the power of 2 is just the part inside. Now I'm going to clean up some more. 64x squared equals 36x squared plus 324. And now we're just going to solve by isolation. So I'm going to bring that 36x squared over. I have 28x squared. Divide both sides by 28. And then we can square root both sides. Now the negative part is not within our domain, so we would reject that value. But I am going to clean up this square root first. So this does reduce to 81 over 7. And if I square root both sides, that's 9 over root 7, which is 9 root 7 over 7. So now time to test. And I'm only testing my critical point because testing 0 and 8 is just option A and B. And when I punch this in, I get approximately 1.33 hours. So this does optimize our time because we wanted the minimum amount of time to get to point B. So, time for my therefore statement. Therefore, the man should row to 9 root 7 over 7 meters away from point C and then run the rest of the way to B. And there we are. So just going back here to our diagram, when we found that x value, this is the value we found. So he's going to row to that 9 root 7 over 7 kilometers away from C, and then run the rest of the way. So for this, we did have to rely on our knowledge that time is equal to distance over speed. All right, next example. A boat leaves a dock at 2 p.m. and travels due south at a speed of 20 kilometers per hour. Okay, so let's say the dock is here, and it's traveling in this direction, south, 20 kilometers per hour. At the same time, another boat heads due east at 15 kilometers per hour and reaches the same dock at 3 p.m., so an hour later. So let's say this is the other one, 15 kilometers per hour. At what time were the two boats closest together? So there's a certain point, at a certain time, maybe this boat is here and this boat is here. And we want this distance to be as small as possible. So I'll label this D for distance. Okay, so I'm going to let X represent the time when the boats are closest together. And because this is all happening within an hour, I know X is going to be between 0 and 1. Now, we already looked at that speed is equal to distance over time equation. But now, because I'm trying to minimize the distance, I'm going to rewrite this equation in terms of distance. Distance is speed times time. So, at time x hours, the boat going south is traveling at a speed of 20 kilometers per hour, and the time is x. So this portion that it has traveled is 20x. Now in x hours, the second boat, going to the east, it has traveled at a speed of 15 kilometers per hour for x hours. But we don't want that 15x portion. I need the portion inside this triangle that I've kind of created, this right triangle. So what would this portion be? Well, the speed is still 15, but what is the time? We know this whole scenario takes place in an hour because an hour later, that second boat is at the dock, which means that second portion of its trip, it's 1 hour minus however much x is. That's the leftover part that it still needs to travel and what time it still needs to travel to reach that dock. So now that I have this is a great setup for Pythagorean theorem. The distance in terms of x is equal to the square root of 20x all squared plus, I'm just going to distribute this 15 in, 15 minus 15x all squared. And this equation is the distance in terms of x, the time. I can now find the derivative of this. and find that critical point. But before I find my derivative, I am going to clean this up a little bit. So 20x all squared is 400x squared. And then I'm going to do distributive property on 15 minus 15x times itself. So that's 225 minus 450x plus 225x squared. All of that is square rooted. Collect some like terms. And I have 625x squared minus 450x plus 225. Now I'm ready to take my derivative with a nice little chain rule. So bring that exponent of a half down, copy paste the inside to the power of negative a half times the derivative of the inside, which is going to be 1250x minus 450. All right, I'm going to set my derivative equal to 0 while I clean this up. So the 1250x minus 450 will go in the numerator, 2 is in the denominator from a half, and then that negative exponent will pop down in the denominator. And now I'll cross multiply, which is lovely because 0 times that denominator is 0, and we're just left with our numerator. And we can isolate for x. So x is equal to 450 divided by 1250, which reduces to 9 over 25, or 0.36 hours. And now we can test some values. So what am I going to test? I'm going to test my distance at 0, my distance at my critical point, and my distance at 1. Well, my distance at 0 is going to be 15 kilometers because the first boat is at the dock and the second boat is an hour away. If it's an hour away and it's traveling 15 kilometers per hour, that must be 15 kilometers. Or I can just replace x with 0 in one of my d of x equations. If I plug in 0.36, I get 12 kilometers, so that's less. And if I plug in 1, I get 20 kilometers because now that first boat has traveled 20 kilometers south, whereas the second boat has now reached the dock. So we can use logic or we can plug into our equation. Either way, the shortest distance is from the critical point. Now, the 0.36 hours, what is that in minutes? If I multiply it by 60, I get 21.6 minutes. If I multiply the decimal by 60, I can get 21 minutes and 36 seconds if I want to be a little bit more precise. So, therefore, at 2:21, 36 seconds p.m., the boats were as close as they would get. And there we are. So in both of the examples we completed, we had to create a nice diagram. There was some Pythagorean theorem involved, and we definitely had to use that speed equals distance over time equation, but we rearranged it for our needs of either minimizing the distance or the time.